Hi, and thanks for joining us for Phosphorus Science Now. I'm Matt Schultz with the Sustainable Phosphorus Alliance. Chemical elements cycle through the environment, and we humans tend to massively disrupt these cycles. We're probably most familiar with these processes in the context of the emissions and sequestration of carbon. Freshwater lakes are among the largest emitters of carbon, but they also sequester large amounts of it through processes that lead to its burial in their sediments. A recent paper in the journal Science Advances explores how phosphorus and nitrogen enrichment of inland waters has affected this rate of carbon burial across some 500 lakes around the world. I spoke with one of the authors of that paper, Dr. Adam Heathcote from the Science Museum of Minnesota, about this work. So, Adam, thanks so much for joining us for Phosphorus Science Now. This was a great paper, and I'd like to hear a little bit about who your collaborators were and where you get funded.
Sure. So this is a kind of been a long brewing piece of work that was thought up between the two other principal authors on the paper, John Anderson from Loughborough University and Dan Engstrom from the University of Minnesota and the Science Museum of Minnesota, now retired. But because of the scale of this project, we were seeking to compile basically the largest ever global data set of sediment cores from lakes. We ended up adding about 20 other co-authors from all around the world, with which together kind of formed what we dubbed the kind of the Global Carb Consortium. So I think from a lot of the authors from Europe, Southeast Asia, North America, pretty much anywhere where they were studying lakes, we put out an emphasis on getting some of the underrepresented biomes, and so we have some authors from those areas. So there hasn't to date been a lot of work done in the tropics, even though lakes there are quite important. And so we reached out to authors who we knew had been working in that area, but maybe hadn't published some of the data we were interested in.
Great. I'd love to hear a little bit more about the research now.
Sure. So I'm just going to quickly talk about why we are looking at lakes in terms of global carbon cycling. Lakes are they do three important things in terms of how we use them to collect data. They're sentinels, so they are always monitoring what's going on around them. So they're not just limited to the perimeter of the lake. Anything that's happening in the watershed or the airshed in some cases is being recorded by the lakes, and they often respond to them very sensitively. They're also regulators, so they're not independent of their environment. They can fix carbon dioxide, they can degas carbon dioxide, they can alter temperature. There's, you can have local microclimates around lakes. And then importantly for a lot of this work is that they're integrators, so that they are collecting data at all times in their sediments. And these data are chronologically sequenced and preserved so that we can actually use those sediments to go back in time and learn not just about conditions as they are right now, but how they were sometime into the deep past. And to kind of just spend a little more time on this lake sediment story. So this is the study, or this is the science that's called paleolimnology. It's related to paleoecology, but specific to freshwaters. And so what we're doing here is actually collecting mud from the bottom of lakes in a chronologically maintained order. This is called a sediment core. In some cases, you have these really nice varves, which is this image on the left. This is a freeze core. And these are basically like tree rings. They're annual laminations. And so in cores where you have these present, you can actually slice and look at an annual resolution. That's not usually the case, though. Usually these varves are not present. They only happen in very specific circumstances. So in most cases, we need to use some other kind of dating method. These cores can be quite long. The one on the left is only maybe half a meter. The one I'm holding on the right is almost 3 meters long. And the importance of these records, as I hinted to, is that in terms of things that are happening now, if we want to put water quality or biogeochemical cycles into context, we need to know something about what happened prior to a lot of the human-related impacts that have occurred. And in most cases, there is no record of that, or very, very sparse records. And so this figure on the right kind of shows this, where you have maybe very short-term monitoring, maybe only lasts a decade if you're lucky, and then you may have some anecdotal or sparse documentary evidence going back maybe several decades, and then basically nothing once you go back, over 100 years. And sediment records from lakes will span this entire time frame, and so they allow you to both contextualize pre-document and pre-monitoring, but then also look at how faithful those records are when you do have monitoring available. And the other reason we're looking at lakes here is that somewhat recently, going back to about 2007, there was kind of a sea change in terms of how freshwaters were viewed in the global carbon cycle. Previously thought to be kind of a closed pipe model, just funneling carbon from the land to the ocean. That has now been revised several times over to what is now called the open pipe model, where we found out that lakes are actually doing quite a bit, and we were missing out on huge stocks and fluxes of carbon by ignoring them. This is one of the most recent syntheses, although there have been several parts to this revised more recently. But the kind of take home in terms of carbon burial is that there was quite a bit of uncertainty. We knew it was important, but it could be anywhere from 4 to 14 grams carbon per meter squared per year, which when you multiply that over the entire area of lakes on the globe is quite a big difference. And also, interestingly, lakes do things quite quickly because a lot of their primary producers are microorganisms. And because of these high rates of processing, even though they only represent about 2% of the area of the global ocean, they sequester up to half of that much carbon on an annual basis, which is clearly a significant amount. So the methods we use in this paper, as I said before, were paleolimnological methods. And so in order to kind of get these temporal trends in the burial of carbon, we had to have some kind of chronostratigraphic marker. And for this, we used a radioisotope, a short-lived radioisotope called lead-210. It has a half-life of about 22 years, which makes it perfect for looking at about the last 180 to 200 years of history, which is kind of what has been recently defined as the Anthropocene. So the epoch in Earth's geologic history that is dominated by humans. And to measure carbon, we used a very simple but widely used technique called loss-on ignition, where we basically burn off all the organic matter at 550 degrees and measure how much was lost by comparing the masses of before and after. And then this was converted to carbon accumulation rates, which is what I'm going to often call the organic carbon burial rate, which will be in a standard gram carbon per meter square per year rate, and that's meter square of lake area. In most cases, only a single core was collected from each of the lakes in this study. I mentioned this was the largest synthesis. There were over 500 lakes included in this study. Previous global carbon burial studies had anywhere from maybe 2 to 100 lakes in them. And all of these were corrected in a systematic fashion so they could be comparable to one another, which was important. And then I'm also going to talk about some landscape variables, which are all kind of upscaled using GIS. Most of them were used using publicly available globally gridded data. So this is for things like nitrogen and phosphorus, fertilizer use, mean annual temperature, precipitation, things like that.
And Adam, when you're talking about this burial of carbon, what's sort of the long-term fate of the carbon, and what sort of timescales does it get turned over in?
Yeah, so when you're talking about glacial lakes, which is the majority of lakes by number at least in the world, then you're talking about a millennia scale burial. So lakes in North America are anywhere from 8 to 13, well, glacial lakes are anywhere from 8 to 13,000 years old. And we imagine that they will still be here with us for at least another few thousand years. So that carbon that is buried there is what we would, at least in terms of a human lifespan, think of as long-term.
Yeah, it's locked up for a long time.
Yeah, so, and I will also mention that we didn't include any data from sediments that were younger than 10 years. And that's because there's been, from some repeat core studies, evidence shown that carbon is not completely decomposed at that point, and so it may lose some to respiration. So those kind of that kind of youngest carbon was excluded because we weren't confident that that was all actually being buried. It could still be, be being actively respired by bacteria within the sediments.
Sure, thanks.
Yep. Okay, and then so since phosphorus is the matter at hand today, I just had a couple of examples to kind of show the importance or the usefulness in tracking carbon burial as it relates to phosphorus pollution in freshwater systems. So this is an example from a lake in Denmark, Knud Sø, where there was a pretty long monitoring record going back to the 70s, and also a well-known point source pollution. So this lake was highly eutrophic, and it was known why. It was being polluted by direct sewage being piped into the lake. And that was remediated, and you see both a drop in surface summer, so this epilimnetic total phosphorus actually monitored in the lake, and that is very, very faithfully tracked by carbon accumulation or carbon burial through time. And this is because most of that carbon that was being buried in the sediments was autotrophically produced algal carbon. And so when the algae declined due to declining nutrients, carbon burial also declined. So this is kind of a useful interpretation to show that, when we talk about carbon burial as a measure of primary productivity in some cases, that this has definitely been demonstrated before.
Yeah, and Adam, I'd assume that you would expect that tracking to even be closer if you were looking at dissolved phosphorus rather than total phosphorus, so bioavailable phosphorus.
Yeah, so if we were looking at SRP like coming in at the pipe, I'm sure that would be an even closer correlation.
Yeah.
SRP is a bit tricky in epilimnetic water because most freshwater lakes are phosphorus limited, so it's basically drawn down as soon as it's available. And so almost all the phosphorus in epilimnetic water is in algal biomass. And so that was one lake, and here's an example from a number of lakes across Minnesota. Minnesota is a good study site, not only because it's where I live, but also because it has a number of intersecting unique biomes. We have everything from tall grass prairie in the southwest to boreal Canadian shield in the northeast. So these lakes kind of run the gamut of where most of the lakes are in the world: temperate grasslands, forests, and boreal biomes. And we see this same relationship across space. So lakes which are more eutrophic have higher total phosphorus concentrations, and more algae also have higher rates of carbon burial. So going to the lakes from this study, many of which were also included in the previous studies, we looked at basically all of the Earth's major biomes. As I said, I think 516 lakes in total. And kind of the real striking thing was that even though the magnitude and the timing changed, we saw increases in carbon burial basically across the board. Certain areas we saw actual declines. Mid-20th century, montane grasslands are an example of that. And we think that has to do with kind of the decline in real fringe agricultural areas. So a lot of these areas are kind of borderline arable land. Whereas we see places like temperate grasslands, where most of the agriculture is done today, continue to rise, and there's no sign of slowing down. On the left here, we see kind of a stacked bar plot of total carbon burial rates in all the different biomes, colored over time in kind of decadal bins, starting in 1900, going all the way to the most recent sediments, which were included in the 2000s. And this accounts for about an additional 72 teragrams of carbon being buried more today than were buried in 1900, which is a significant amount. That's like almost 0.7 gigatons. And so we know carbon burial is going up in lakes all across the globe, and so we wanted to look at some of these coincident, co-occurring global drivers. And some of the obvious ones to look at, because we know that carbon burial is closely tied to nutrients, were global use of phosphorus in fertilizer as well as nitrogen, as well as global temperatures. So we know that productivity is temperature controlled because it's a metabolic process. And so we would expect more production of algal biomass with warmer water temperatures. And then we also wanted to look at just land clearance. So as you clear land, at least initially, you often get large fluxes of terrestrial soil carbon into lakes as you lose that perennial deep-rooted vegetation and either go to some kind of agricultural rotation or alternate vegetation. And what we saw is that they followed very similar trends to carbon burial, at least in those temperate grassland and formerly forested areas where we see exponential increase in fertilizer use in the mid 20th century, correlating with the increases in carbon burial in those areas. And when we look explicitly at nitrogen and phosphorus fertilizer use globally to lake global carbon burial, we see kind of interesting correlations between the two different nutrients. We see a saturating relationship at very high nitrogen use and a kind of linear but maintaining correlation with phosphorus, which kind of reflects what has been documented in most freshwaters as being P limited worldwide. So as we saturate the world in nitrogen, we only enhance that P limitation of our freshwater systems. And so we were interested if we could develop a predictive model for global carbon burial based on kind of these global nutrient fertilizer use, as well as temperature models, because as I mentioned before, there's reason to believe temperature would also be important. And kind of interestingly, even though temperature was significantly correlated to global carbon burial, it explained a very low amount of the variation in our temporal data set, only about 4%. The real big explanatory power came from when we introduced these nitrogen phosphorus fertilizer use. Each one independently explained about 20% of the variance. And together this model explained about 44% of the variance in carbon burial over time. And so this is kind of the story of why we believe, or at least this is what the correlation is showing us, carbon burial has gone up in the last century to century and a half. And then the other piece of the puzzle, which isn't explicitly related to nutrients, is that the other reason we've gotten a lot more carbon burial is that we've significantly altered the hydrological landscape, most importantly, the production of reservoirs. So added on top of those natural lake carbon burial here, we've now added the amount of area in reservoirs and an average reservoir burial rate. You can see it almost doubles when you add just by adding more lentic aquatic systems, you almost double the rate of carbon buried by lakes. And so some take-home messages here. If you hadn't got the memo yet, lakes are indeed important sites for carbon processing. Ignore them at your peril. And carbon processing in these systems is significantly altered by nutrient inputs, specifically nitrogen and phosphorus, but also it's been shown silica and sulfur. And kind of interestingly, in terms of where they fit into the global carbon cycle, there's this unidentified sink of terrestrial carbon fixation. And by adding this additional piece from global freshwater lakes, we can start to chip away at that unidentified sink. So it's a missing piece that wasn't considered, at least at the turn of the century, and is now being increasingly considered and quantified. So that's all I had.
Great.
Matt, I'll take any other questions that spawned.
Yeah, thanks, Adam. There are a bunch, but I think the one that I'm focused on is, we've done a lot of talking with John Downing and other folks who've been looking at emissions from lakes in recent publications and looking at how inland waters are such huge contributors to greenhouse gas emissions. And this is kind of the other side of that, right? So there's the carbon burial part. So you've got sequestration and emission. Can you balance those out for us in terms of scale?
Yeah, sure. Luckily, I'm prepared for this question because John Downing was my PhD supervisor.
Great.
So we estimated in this paper, if you looked at just CO2 emissions, when you sum modern or contemporary carbon burial in lakes and reservoirs, it accounts for about 30% of the emissions. So it's still a net source. And so since we've also shown that carbon burial will increase with eutrophication, and there's been kind of conflicting evidence of what will happen to CO2 emissions. Some papers have shown that it will decline. Others have been shown that it will increase. But certainly methane will increase, as you said. And the most recent estimate done by John Downing and a couple of other co-authors estimated that in the next 100 years, it's going to be something like 1.5 to 2.5 additional petagrams of methane carbon equivalents degassed from lakes due to eutrophication. So this just blows any increase in burial completely out of the water. I mean, we're talking about total burial rates of something like 0.1 petagrams.
Yeah. Okay. So the take home there is the solution to climate change and is not more eutrophication. We shouldn't be pumping nitrogen and phosphorus into our waters in order to control climate.
Yeah, even if that was a good idea, it still wouldn't work.
Yeah, right. Of course. Okay. Well, thanks so much, Adam, for a great presentation. And thanks for joining us for Phosphorus Science Now.
Thanks, Matt. It was a pleasure.